Okay, let's give this example a shot where we're trying to find dy dx. And it's kind of interesting looking problem. Looks like we have several terms going on here, some x's and y's throughout, but things that stand out, I notice that we have y to the fourth multiplied by another function here. And this other function with the natural log has a function on the inside of it. So it's going to make this a little bit more challenging than if these were all separate terms that weren't connected with, functions inside of functions and multiplications. So let's attack from the beginning here, get our approach down. Because those are multiplied together, we're going to have to use the product rule. And I'm going to think of our first function as being y to the fourth, and our second one as being this natural log of x to the eighth power. So let's list out what the product rule is going to look like. Well, in this case, it's going to be f prime times g plus f times g prime. And as we take these derivatives, we're using implicit differentiation. If our variable is a y, we're differentiating everything with respect to x. We need to be sure to write dy dx whenever we're taking the derivative and our variable is the y. All right, so one term at a time here. First of all, f, our y to the fourth power. The derivative there is just going to use the power rule, and we're going to go 4 comes down in front, and then we reduce the exponent by 1. So 4 minus 1 is going to give us 3 for our new exponent. But then we do have to be careful, because our variable was y, next to this being multiplied, we're going to include a dy dx. I'm going to try to highlight these as we write them. That's why I'm putting them in blue. Okay, next we want to multiply this by g. Well, this is a copy down step, where we go natural log of x to the eighth without actually taking its derivative. Plus, now it's copying down y to the fourth power as f, but then we need to multiply this by the derivative of the natural log of x to the eighth. Well, because we have a function inside of another function, we're going to have to use the chain rule to accomplish this. So the chain rule says we deal with the outer function and take its derivative first. So in that case, it's natural log, which its derivative would be 1 over whatever's on the inside. But then you also have to multiply by the derivative of the inner function. So in our case, the inner function x to the eighth, we can use the power rule again, bring the exponent down, reduce the exponent by 1. All right, because our variable was x and we were taking a derivative, we don't put a dy dx next to it. We will simplify that down in a little bit, but I'm going to keep moving on. Taking a look at our next term, we have 4x to the 10th power. So as we think about taking its derivative, it again is going to be the power rule. We have that number out in front, so as we bring the 10 down, we'll go ahead and multiply that by the 4. So that'll give us 40. Then our variable was x. Reduce the exponent by 1. 10 minus 1 is going to give us that 9. Now we have minus y to the 9th power, so I'm going to bring the negative along. Power rule here is going to bring the 9 down in front, keep the same variable, and reduce the variable by, or the exponent by 1. But do be careful in this case. What we ended up with here, we were taking the derivative of a y as our variable. So that means that we have to have a dy dx next to it. All right, finally, on the other side, we have this negative 1. So that's going to be a constant. The derivative of a constant is going to be 0. All right, from here, really all we need to do is we'll do a little bit of reducing down as we go. But the end goal on this is to get dy dx on one side by itself. All right, so as we think about that as our end goal, let's get all the terms that have dy dx on one side and all the terms that don't have dy dx to the other side. So as I think about reducing down maybe before I move over, I'm looking at this middle term here, this one going on. We've got some x's in the denominator. We can think of the x to the 7th as being up in the numerator as well as that 8. Well, we can simplify that a little bit by saying, well, these 7 are going to cancel out with 7 from the denominator. Therefore, we'll be left with 1 down in the denominator. So as I'm thinking about moving that term over, it's positive right now. I'm going to suggest we subtract y to the 4th power times 8 over x. We can clean that up even more by writing it as minus 8 y to the fourth power all over x. But to move that to the other side, we're going to subtract it from both sides. All right, the next term I'm going to focus on, this one doesn't have a dy dx with it. So I want to move it to the other side as well. We're going to subtract 40x to the ninth power over to the other side. All right, in doing so, these will cancel and these will cancel, so they won't be on that side anymore. Let's take a look at what remains on that side. As I write these, by the way, on each term, I'm going to go ahead and leave the dy dx kind of in front of the term because we can rearrange because everything's multiplied together inside this in the single term. So we still have 4y to the third multiplied by the natural log of x to the eighth from that first one. And then we have a subtraction. Again, I'm going to move that dy dx out in front. And that's being multiplied by the 9y to the eighth power. And over on the right-hand side, just copying down what we have over there, 8y to the fourth power over x minus 40x to the ninth power. Okay, as you work on these, you're going to get the hang of, after you get all the terms that have dy dx on one side, what we want to do next is factor out that common factor. So because they each have a dy dx, let's go ahead and factor that out of each one of these terms. So that's going to give us a big set of parentheses, 4y cubed times natural log of x to the eighth minus 9y to the eighth power is still equal to just copying down exactly what was already on the right-hand side. All right, at this point, we've set ourselves up that we have dy dx multiplied by this big set of parentheses. So all we needs to happen to get dy dx on one side by itself is to get rid of that big set of parentheses. Because of the multiplication, we'll use division on both sides to accomplish this. So we'll divide both sides by 4y cubed times natural log of x to the eighth minus 9y to the eighth power. Just copying it down over on the other side as well. All right, in doing that, multiplying both numerator and denominator by the same thing, these are going to get to cancel, and that'll isolate the dy dx on the left-hand side all by itself. Now, I will admit what we have on the right-hand side, we could clean this up a little bit if we wanted to. I don't think it's really necessary, but if you don't like seeing a fraction within a fraction, one option in this case would be multiply both numerator, the entire numerator, and the entire denominator by x over x. All right, what that could do for us is it would eliminate the dividing by x in that first fraction as we distribute this to each one of these terms. All right, so as this x gets distributed to each one of these terms, we could clean up our answer slightly and say dy dx is going to equal, well, when we distribute to that first one, the x's cancel out because you're multiplying and dividing by the same thing. And that was kind of the goal on this. Distribute it to the second term. Well, we had 9 copies of x. We're multiplying by an extra copy, so that'll be x to the 10th power. Now, we also kind of probably want to distribute in the denominator. I don't know. It's just depending on how you want to see this look. If we did distribute, we'd get an x with this first term. Everything else is still involved with the same first term. And we'd get an x with the second term as well. All right, so a little bit nicer instead of having fractions within fractions. You didn't really need to distribute the x along in the denominator to make it look any nicer. Just personal preference, really. So I hope this helps out as you're working on implicit differentiation. Good luck with it.